My name is Philip. I run a company called LogNormal that does real user performance measurement. What does that mean? That means we measure how long it takes page to load from a real user's point of view. So put some JavaScript in your web page, and which loads up in the user's browser, measures the page load time while they're surfing your site, and then we send it back to us and do a bunch of analysis on this. I'm a web speed freak. I've been doing web performance for several years. I was at the Yahoo Exceptional Performance team, the group that brought out Rise Slow and Smush It, and a whole bunch of performance rules. So a lot of what I'm going to talk about today is stuff we've developed at Yahoo, or the techniques we developed at Yahoo, and that I've taken forward for building up the product at LogNormal. I'm going to see if this thing works. I'm using this as my remote. Where are my arrow keys? LogNormal. So we measure real user website performance, and this talk is about the statistics we do to measure it. Was anyone at my talk last month? All right, so last month we spoke about how we actually do the measurement, the JavaScript code that sits on the page and measures it and sends the data back to your server. Now that code is open source, so anybody can take it and run their own measurement if they don't want to get me to do it or somebody else. This talk is going to tell you how to do some of the back end, so if you actually do want to build your own service, you can go ahead and build an end-to-end service on your own. Right? So basically giving away my technology for free. So, statistics of web performance. That's the date, right? A lot of what I'm going to talk about today I also blogged about yesterday. So I'll have a link to that at the end of my slides. And I guess we posted on the Meetup page as well. So if you want to go ahead, and if it's might get too heavy during the talk, so if you want to go ahead and read it at your own pace, that's also possible. So numbers. Who knows what numbers are? What are the numbers we care about? That's what I'm going to talk about here first. So what we're trying to do is accurately measure page performance. So we need some number that we, as a developer, as a performance engineer, I show to my boss and say, hey, this is our number. We're better than yesterday, or we're worse than our competitors or something. So what's that number that you use to quantify your performance? And how do you actually measure that accurately? So we want to accurately measure performance, and I've got a little star there because of Heisenberg's uncertainty principle. If you try to measure something accurately, you change the measurement of something else that's real. Heisenberg's principle is associated with position and velocity, but it in fact affects everything. If you try to put a measurement beacon in a page, you're going to affect the performance of that page because you then have to load the code that measures it. So how do you do this as fast as possible, or as unintrusively as possible, and get one number out? What's the number we're trying to get? Well, we have three numbers here. Any one of them is useful. Network latency, which is what a lot of monitoring looks at. It's how long does it take your server to respond, right? If you make a request, how long does it take to get a response back? And that typically depends on how far the user is from your server, how much work your server is doing on the back end before it can respond. Network throughput typically depends on how fast the user's pipe is and all the way from their computer to you. So if they're running on a slow dial-up connection, their network throughput is going to be low. If your server is on a dial-up connection, it's also going to be low. And I've seen companies that have servers on dial-up connections. Not right now, but back in the 90s, that was not very uncommon. So we're not going to, again, I spoke about how we measure these in my last talk. Today I'm going to do how we analyze them. So we measure real user data, which is noisy. Right? You have users coming from all over the web. They have different kinds of different computer systems, different operating systems, different network connections, different amounts of software installed, plugins in their browsers. Some of them are infected with viruses, some of them are infected with antiviruses, and some of them have open wireless connections, so their neighbors are stealing their network. So you really have no one defined set of characteristics that your user is using to connect to your website. They're coming in from all different kinds of network connections, and you're definitely not going to get any. So the only thing that's certain is there's not going to be consistency in the data you get. Right? So you have to do some kind of analysis on that data to figure out what's my one number. If you don't, you're going to have 1 million numbers. Right? And that's not very useful. So, statistics 1. Disclaimer, I'm not a statistician. I am a computer engineer. I learned most of my statistics in high school and forgot it when I entered college. And then I learned it again from Wikipedia and the various statisticians that worked at Yahoo. So a lot of what I'm going to talk about is what I learned, and I wrote down a lot of it while I was learning it, so that's what these slides and the blog post are all about. So, random sampling. Does anyone know what random sampling is?
Just randomly taking a small percentage or some percentage of users to...
Right. So take a small percentage of your users to get your data. Why do we do it? Because typically we might, our entire user base might be too large to measure. A good case is just looking at opinion polls for the elections, right? You could go and ask every single American who they're going to vote for. That's called an election, right? Or you could go in and say, from every city I'm going to pick up maybe 100 people and at random meet them on the street and ask them who you're going to vote for, and based on that extrapolate to what the whole country is going to choose, right? So that's a random sample. You randomly pick a small subset of your entire population and say, I'm going to base my entire measurement on these people. So this is what our entire user base might look like. Right? A whole bunch of trees around. I think this is the Amazon. Could also be someplace else. A representative subset is typically something that's randomly. It's completely random. So there's no. If you just go to Starbucks and interview everybody in Starbucks, you're only going to know what people who go to Starbucks are going to choose, not people who go to Dunkin' Donuts or some other place, right? So you really want something that's completely random across your entire user base. Sometimes you pick something that's representative, sometimes you pick something that's not. So you end up with people all clustered around, or users all clustered around a particular, some other feature. You might actually only be measuring that, and that's going to skew your results. You're not going to know why that's being skewed unless you actually examine how you're coming up with your user base. So how would you go about randomizing? Any ideas? Well, XKCD solved it for us. So one thing we do, there's two ways we could randomly sample. We could pick 10 users at random and always test them, and maybe change that sample every day or every week so that we're not stuck with the same 10% of users. Or for each user, give them a probability that they're going to enter the sample or not. And in the first case, we need to do something like session IDs, because we want the same user to be in our test bucket for every single request going forward, right? Whereas in the second case, we do it on a per request basis. So what would the code for that look like? In the first case, some kind of session ID. It could be based on, you could generate your session ID anyway, you need to be able to do a modulo something on that. And if it comes out to a number, I've chosen 0 here, but you could take anything from 0 to 9, the probability is equal. If that session ID matches that particular parameter, then we say, okay, we're going to instrument this code for measurement. If not, we're going to leave this user alone. So through that, we picked up 10% of our users. As long as your session IDs are generated uniformly across all of your users, this kind of guarantees you're going to get 10% of your users. Not 10% of hits, but 10% of users. Right? You might get the 10% most active users, which means you're getting way more than 10% of hits. Or the 10% least active users, which means you're getting way less than 10% of hits. Right? That's something else called confounding that I'm not going to cover here because it's so confounding I don't understand it. But basically, it means if you uniformly assign session IDs, you'll get 10% of your users, right? And that's what we want to measure, right? The problem is you might pick the the wrong 10% of users, right? They're not sufficiently random. So you'll end up getting positive feedback if you keep using the same set over and over again. So you'll measure them, you'll get some reading, you'll react based on that reading, improve performance based on that, and then you're testing the same 10% of users, So you're just getting positive feedback, and everyone else is not getting tested. So what you want to do if you do something like this is change your sample every week. Right? This week I'm going to run 10%, the next week I'm going to generate 10% using something else. So maybe I pick 0 now, I pick 1 as next week's parameter, and so on. The other option is just for every single page request that comes in, give it a 10% probability that it's going to be measured. Right? So the simplest code is if random less than 0.1, ignore that get rand max, that's PHP code, but if you're using something like JavaScript or C, which gives you random numbers between 0 and 1, and you just say rand is less than 0.1, which gives a 10% probability that that particular request is going to be measured. Right? This means that a 10% probability does not guarantee 10%. Right? It could be, it could just be that in 90% of your cases, your random number does in fact become less than 0.1. This is not unknown. That's why they call random numbers, right? Because you cannot predict what they're going to be. So there's a 10% chance of it being tested, but that does not guarantee that you're going to have 10% of your population. What it does guarantee is that it's going to be random enough that you're not going to get this kind of positive feedback. The same user is not going to be in your test on every request. So user A comes in and gets measured right now. You might click on another link in a minute and not be tested for that link. So that's what happens with this kind of testing. Both of them have their pros and cons, depending on what you want to measure. So if you want to measure session times, then you definitely have to do the first case. Or you do the second case with something like a cookie, which says, once this user gets into the sample, they're going to stay in the sample for 30 minutes or something like that. So, how big a sample do we need? We've said 10% here, but 10% for Wayfair may not be 10% for someone else, right? It all depends on how many page hits and how many users you have on the board. So what we typically say is you select n, which is your total sample size, to be modulus 1.96 sigma, which is your standard deviation, divided by root of sample size should be less than 5% of your mean, right? This formula is based on 95% confidence interval value for a normal distribution. So it basically says I'm 95% confident that this sample is representative of my population. And you want n to be that. So if you have 1,000,000 data points, and you pick 10%, that's 100,000. So is 100,000 good enough to get you this number? If not, you want to go to 20%. If it's really good, can you go down to 5%? Right? And you can pick, you only know that after you've actually done some amount of testing. And you keep feeding back into that loop. So you can adjust the sample based on the error that you're getting. Now I need to mention that you don't do this at the top level. So you could say, Wayfair.com has got so many million beacons, so I only need a small sample. You want to see the actual level you want to go down to. So how many people come in from, let's say, Wyoming using Internet Explorer 6 on a DSL connection, right? You want your sample size based on that drill down level. That's as far as you're going. If you're only looking at it at the top level, then fine, just pick your sample size at the top level. All right, so margin of error. I spoke, this function deals with margin of error, but what is in fact margin of error? So if you look at a normal curve, that's the standard deviation tells us spread, right? The mean tells us where exactly that curve is centered. The standard deviation tells us how wide or how narrow it is. The margin of error tells us how confident we are that this particular curve fits our population's curve, right? And that's the formula. So there's an inverse square correlation between sample size and error. Naturally, increasing sample size reduces your error. Theoretically, it should. Central tendency. Any ideas what central tendency means? So when we talk about central tendency, we really want to see where our users are clustered around. Right? Are they completely spread across the spectrum, or are there clusters within our performance characteristics that most of our users fall into? So when we look back at this bell curve, the central tendency is right there in the middle. So typically between -1, plus and -1 standard deviation is where most of our users are centered. 68% of our users fall in there. When we're building websites, 68% of our users may not be enough. We may actually care about 98% of our users. Or we may care about 50% of our users, depending on how far on the performance investment curve you are. So these are different curves, bell curves, showing different standard deviations and different medians. Central tendency moves based on based on the mean. So in this case, in the green line, it's -2. In all the other lines, it's 0, even though standard deviation is changing. Now that may not always be the case for your curve, and we'll look at some actual curves that we see in practice. So this is where we come in with the one number, right? One number that you're going to give up to your boss, or that you're going to put on your performance reports that should show up every day or every week. What's that one number? So we have different numbers that we use for defining central tendency. Before I say that, okay, a lot of people use the term average, right? What does the word average mean? Average means mean. So in general parlance, average means mean. When someone says the average, they mean the arithmetic mean. Take all the terms, add them together, divide by the number of terms, and that's the average. Statistically speaking, that's one average, right? That's not the only average. Average is an overloaded term in statistics. The arithmetic mean is one type of average that you could have. And you get that by adding all the terms and dividing by the number of terms. So in this case, of these data points, the average or the mean is 30. There's also the median, which is also an average. Right? It's the centermost point of your data set. Now the way you get this median is to take all your data points, sort them in ascending or descending order, and take the middle point. It doesn't matter what order, because the middle point is still going to be the middle point. That's fine if you have an odd number of points, right? You have a middle point defined. What happens if you have an even number of points? Right? In this case, I have 5 points, so the median is obviously 11. If I had 6 points, then we have 2 middle points, the third point and the fourth point. So I take the arithmetic mean of those 2 points and say that's my median. So in almost all cases, the median is in fact part of the data set, except in the case where you have an even number of points. I guess on average that would be in 50% of the cases the median is part of your data set. Right? When you deal with really large data sets like 1 million, 2 million, 5 million data points, it really doesn't matter if you're doing the middlemost point or 1 point to the left or right. They're so close together that it doesn't matter. Right? In fact, in most cases they are the same. Right? So you can just simplify your arithmetic and say take all those data points and just find the closest one in the middle and use that. Total index divided by 2, that's the point. We have the mode. The mode is the most popular term. So in French, mode means fashion, and a la mode means in style, and the mode in terms of statistics is the most fashionable number in the data set. So the one that occurs the most often. Again, when we look at it theoretically, we pick the most popular term. Now, in this small set of 5 points, 11 is the most popular term. But when we have something like 1 million data points, we might get several points that are not necessarily the most popular, but are the most popular among the points around them. Right? And we'll look at an exact curve, I think pretty soon now, to see what we talk about. A percentile is another way of, another number we can use. It doesn't define central tendency. It defines something else. So you could say 25th percentile is what my 25% most fastest users experience. Right? So 25th percentile of the curve, and you can do that to say, okay, what's the best that people are experiencing? But you might also look at 75th, 95th, 98th to see what's the worst that people are experiencing, and try to bring that down. So you want your middle point to be good, but you want your 98th percentile to be not bad. You want that to be sort of tolerable. Otherwise, you're still losing people. And then there's the geometric mean. And just like the arithmetic mean is the sum of all numbers divided by the total number of numbers, the geometric mean is the product of all numbers taken and the nth root of that product. So, I'll show you the formula right now. It's nth root of product I is equal to 1 to n of xi. Right? The problem with this is it can lead to overflow. If you multiply too many numbers on a computer system, you will in fact exceed the largest data size an integer can hold. Right? So what we do is we use logarithms to simplify it. The cool thing about logs is that a product of numbers, you can just, if you take the log of a product of numbers, is the same as the sum of the logs. So you could just take the log of each number, sum it up, which take the arithmetic mean of that, and then take e raised to that. So on the whole, you don't use up too much memory. You can in fact do this much faster because now you just need to store a sum, a running sum. So if you're getting in 1 million data points, you don't have to store 1 million data points. You have to store the sum of their logs and the number of data points. You need to hold on to 2 integers, well, 2 doubles in this case. And then at the end, take e raised to that. So it's computationally simpler, uses less memory, and doesn't overflow. So we typically end up with this particular calculation. There's also something called the harmonic mean. In fact, there are more means. We don't look at any of those in terms of performance here. These are the four that matter. And consequently, for each of those means, there's a standard deviation and a margin of error, which we're going to ignore. So, what do these distributions look like that, and which of these means, or which of these averages would be used for different kinds of distributions? So, this is my blog. I don't get many visitors to my blog. Please change that. But basically, I've got users from around the world, maybe like 1 user from India, and 1 user from Malaysia, and 3 users from the US and stuff. So we got a few different points across the map, and it's actually going from 0 to, I think, 10 seconds there. So somebody got a 10-second load time, a few people got something between 0 and 3 seconds. So I don't really know what my distribution is, right? I mean, what do I optimize for? It doesn't make sense. I don't have enough data to statistically analyze this. This is 100% of my data points. I'm not doing sampling on this. So my margin of error is pretty high. It's something like 50%. There's no way I can get any insights out of this numbers. And to be honest, if you're at this point in your development cycle, performance is the least of your problems. Distribution is probably a bigger problem that you need to worry about. Something more common is what we see like this. This is a data set of 5.5 million points. Right? I haven't put numbers here because the numbers don't matter. Right? When you're looking at a histogram, or this is more like an area histogram curve, probability density function. The actual values there, whether it goes from 0 to 5 seconds, 0 to 10,000 users or 20,000 users, doesn't matter. It's the percentage of users and more the shape of the curve that matters. So this is running from 0 to 20 seconds. Bulk of the users are falling in here around 5 seconds. I know that because I know the actual chart behind this. So you take my word for that. So this is more representative of what you get for most users, for most websites. Anything larger than maybe 10,000 data points, you are going to see a curve like this. That's because the bulk of the users have fairly typical behavior here. Few users are extremely fast, or they might have ended up with error pages which tend to load pretty fast. Or they may end up really slow because of some infrastructure problems, temporary problems, their Wi-Fi disconnected, something like that. So you'll get a few users on that skew. But most of them are in this center. And this particular distribution is what we call a log normal distribution. It's called log normal because if we take, instead of plotting the number of data points versus load time, we plotted number of data points versus log of the load time, we'd end up with a perfect bell curve. Right? Something similar to those initial diagrams we saw. So the log of the distribution is normal in nature. Now we also see things like this. which is somewhat of a bimodal distribution. Right? We see one peak here, and we see another somewhat smaller peak there. Right? Strictly speaking, this is not a bimodal distribution because those two are not equal. Right? But it's they're local maximas. Right? It's like when the curve is moving down, it suddenly starts to move up again. So we know there's something else is happening there. And typically you see this kind of a distribution when there's two distributions superimposed on each other. Right? So there may be two different things happening here. And one case where we've seen this happen is people do a lot of back-end caching. So they cache content, they cache their database results in Memcache, or use Varnish on the server side. So the first curve you see here is from a warm cache, the second curve you see there is from a cold cache. So if you get a 50% cache hit ratio, you're going to see equal distributions. If you have a 75% cache hit ratio, that curve is going to be smaller and more to the right, right? And so on. And we know this because we've gone deeper into that and seen like time to first byte and gone back into the back end and analyzed that kind of data.
So may I ask?
Yeah.
If you go back to the one more on this slide here,
yeah.
I realize it's illustrative, but what are they called? Intervals along the x-axis?
Right.
How do you come up with the intervals or buckets or whatever they're called for that? Like
So,
like this?
so it largely depends on two things. One is how much memory you're willing to devote to storing that frequency table.
Okay.
And the second is how much of a resolution you want. So in terms of web performance data, if you're looking only at page load times, if your typical page load is something like 3.3 seconds, so running from 1.5 to 5 seconds, you can do with something like a 300 millisecond or 500 millisecond bucket, because that kind of it doesn't spread out so much that it's going to take smoothing your curve, but it gives you enough of a resolution. If you're looking more at things like DNS time, TCP time, which are already small, you might look at 1 millisecond bucket. We can't go below 1 millisecond because that's our least measurement.
So then I guess I was asking, is that more of an art than an actual like formula, number of standard deviations or something like that? Or?
Yeah, it's so like I said, given enough memory, you could just go and say I'm going to do 10 milliseconds for everything. But yeah, it's more about knowing your data and then based on what your experience kind of falling back on that. So we actually do 115 millisecond buckets for load time, 1 millisecond buckets for things like DNS and TCP. But then our caps are different. So for load time, it's 20 seconds, whereas for DNS and TCP, it's 100 milliseconds or 300 milliseconds is the cap.
Philip?
Yeah.
On that same chart, I know it's just an example, but...
Which one? This one?
Yeah, this one.
Sure.
It just looks to have a very long tail.
Yeah.
Is that in any way normal of what you see, or is it just an illustration?
This is actually normal. The tail will actually go beyond the right side of the chart. So the chart goes from 0 to 20 seconds. And you might actually see a 98th percentile somewhere at 130 seconds, right? 2 minutes. Because there are pages that do take that long. An example, I have seen one case where the user's DNS server timed out twice. They had 3 DNS servers in rotation. The first 2 timed out and the third one returned the IP. So it was 30 seconds for each timeout, which means they lost 60 seconds just on doing a DNS lookup. So you will actually end up with some results there just because of these things that you can't control. So it's not atypical. Those are really like one data point or something going all the way there. Yeah.
Would it ever make sense to use different size buckets at different ends of the spectrum? Like use 10 nanoseconds on this?
We do actually do that. When we render it, we render it at 151 seconds. So I mean, if you did like render 10 milliseconds here, you wouldn't see the difference between them. Simply because the chart is too small to actually see 10 milliseconds in a 0 to 20 second chart. If you zoom into that, then you might be able to see that.
So you can zoom farther in on the smaller.
Yeah, we don't offer that right now, but like I can do that myself. Use R or something to go to the data. Yeah.
You mentioned this is the log normal.
Yeah.
So what does the logarithm do? If I didn't log it, wouldn't I get the same
Same
shape.
the same shape?
Well, if you we're not doing the log right now. If we did a log, we get a perfect bell curve. So
Oh, so this log normal is not log.
It is a log, yeah, this is not log. So I'm just doing a linear curve on this.
Oh,
If I did do an exponential log curve, then I'd see it symmetric over a certain point.
And that was the logarithm of the
x-axis, the load time. So, yeah, this is pretty much what I always say. So, bimodal distribution is not uncommon, and you guys just start getting a bimodal
Notice
distribution.
that. Yeah.
Should I show the chart later?
Sure.
So, typical reason would be because you're doing back-end caching. There could be other reasons as well. You might have a that's bad or a bad switch. We've seen that as well. One particular bad switch which has high latency and 1/3 of every request. So in that particular case, you're going to have a bad load time show up. And that's going to look like a bimodal distribution.
And I'm sorry, I just confessed if you explained what a bimodal distribution was, then I didn't catch it because I was thinking of my question for the previous chart. So what is...
So this is either bimodal, or we might also see multimodal distributions where we have two peaks. Right? Now theoretically we say when we call it a peak, they have to be
that's just the
equal.
result of some data. It's not something that you did to create the I gotcha.
So whatever data we're looking at, we plot a histogram, and that's when we know what the distribution is. We try to fit that to a well-known distribution formula. In all cases, they may be a summation of 2 or 3, and that's what you'll see. So the complicated ones are when they do back-end caching and they have a bad switch, because then you have like 4 peaks, but you can't tell the difference between them, because sometimes they happen at the same time. Like you'll have the cold cache and the bad switch show up, and sometimes you'll have them at different times, so it looks like pretty flat at the top until you go and drill down further and see what's happening. So, filtering. What are we doing on time? 10 minutes? Is everyone still awake?
Yeah.
So, outliers. And that's what we were talking about a little earlier about the long tail. That's when we have outliers. So they're out of range data points. And they could be either really fast data points that are unreasonably large, like my page loaded in 50 milliseconds. That typically doesn't happen unless they were loading it out of cache, which could happen, but it's unlikely. It might also mean that they got a 500 error. 500 error, we wouldn't get a beacon because there wouldn't be anything there. But you could have got a 404, so it just returned immediately and took 100 milliseconds because there's nothing on that page to draw and stuff. So you might want to just take those out and say, they're not representative of my site, I'm going to ignore those. You might also have really slow data points that you can't control because DNS error, the user's Wi-Fi connection dropped while they were trying to load up your page. And so a lot of things happen that are out of your control that you want to ignore. So you may not be able to fix them, right? But you want to do something about them. You want to filter them out so that they don't affect that number you put on your report. They don't stress you out when you're trying to improve performance and nothing's happening, right? Or your 99th percentile is not getting better. It's because there's that one user who has his modem sitting on top of his microwave oven, and there's nothing you can do about that. So DNS problems cause outliers. There's a paper about that if anyone's interested in reading. It's from 2002. I forget whether it was a joint paper between MIT and University of Seoul in South Korea. So that results in a load time. There may be other things like I mentioned. The first kind of filtering we do is bandpass filtering. Any electronics majors here? Electrical majors? So bandpass filtering is typically something you do when you have a data set, multiple frequencies in it, and you want to restrict it to a single, like it's a bass control when you amplify, right? You turn up the bass, you're only filtering through low bandwidth So in the case of performance data, we say, these are my same data ranges, and I'm going to strip out everything outside that. Right? So anything less than a page load time of 50 milliseconds, you might want to strip out. Page load time more than 2 minutes, you might want to strip out. So it's not like these things don't happen, but page load time of more than 2 minutes might happen. It's just unlikely that a user is going to wait around for 2 minutes for a page load. We've seen page load times of, I actually saw one page load time of 7 days. The only explanation I can give is that the user started to load the page, closed their laptop, and left it closed for 7 days, and then opened it up, and that's when the beacon went through. That's just speculation. I can't actually prove that. There's also bandwidth ranges. So we set a bandwidth range at 4 kilobits to 4 gigabits. We haven't seen anyone, or we haven't seen a large number of data points with 4 gigabits, but it's possible it will happen in the near future. We have seen one data point with 1 terabit data connection coming in from Sweden. We believe it might be anomalous. So you may need to relook at these ranges simply because infrastructure improves over time and bandwidth values may get better. You may also not be able to define a range for a particular, for like all of your users. Like users from the US may have one range, users from India may have a different range, simply because of the infrastructure available in those two countries. So what we then come up with is something called IQR filtering. So IQR stands for interquartile range, which basically looks at your distribution. Again, we have a bell curve here, and it takes the middle 50% of your data points. So everything from Q1, that's your 25th percentile point, to Q3, which is your 75th percentile, and defines a range called your interquartile range. And then based on that range, we filter our data points. So the way to do that, I'm not sure if I have that actually. So the way we do that is we take the interquartile range, multiply it by 1.5, then take Q1 minus the interquartile range, that number, what we call the field width, and Q3 plus the field width, and then only accept points that are within that range. So Q1 minus FW to Q3 plus FW. Everything else we strip out, and it typically comes to between this and that point. So we're leaving out something just past, just below 3 standard deviations. And that gives us a good enough middle amount of our data. We stripped out outliers that we possibly can't do anything about. And in reality, you may not strip them out, you might move them to a different data set and say, analyze later. When later comes, we don't know. It depends on how much time you have. But this is the bulk of data that you actually want to analyze first and try to improve your performance based on what these users experience. Right? This is true for a normal curve. In the case of a log normal curve or a bimodal curve, it will be the same except skewed one way or the other. That's more or less what I have. The whole, almost everything I've spoken about today is at this blog post, which I'll post the link to that on the Meetup site. There's also a lot of references here. So I initially started by putting all the list of references here, but there were so many that the font size grew really small. So instead, they're all on this blog post. If you go to the blog post, don't even read the post, just go to the references on the right. they're right on the top, so you don't have to like scroll down to the bottom. And summary, what do we want to do? Choose a reasonable sample size based on your margin of error. Decide based on your data what kind of a middle point average you want to use. In most cases, it might be the median. Sometimes it might be 2 medians or 2 modes. And figure out what kind of distribution, so whether it's normal, log normal, or something else. And based on that, whether you actually need to worry about performance improvements or something else. And filter out anomalous outliers. That's all I have. I'm Philip Tellis. My email address, if you need to ask me questions, I'm also on Twitter. And we do log normal. If people are interested, I can show you what some of the graphs look like that we get out of this. Anyone interested?
Yeah. Yes. All right.
Thank you. So again, I'm going to show you Wayfair's chart because Jonathan says it's okay. My other customers don't say it. That's what it looks like. We have, again, you see here the bimodal distribution, so there's one thing there. That's most likely because you're doing backend caching, Varnish or something like that.
We're not. That's
I
a
know.
really bizarre few 8 seconds. I don't
Right.
know about that.
Oh, we can analyze it further.
Yeah, we should.
What is this about? This is your...
This is Wayfair's page load time.
That was the entire site.
It's the entire site.
Yesterday.
Oh, I got you.
So the median load time, which is pretty good. That's the error that we've calculated, 0 seconds in this case, because almost 2 million data points, you're unlikely to get any error in that. Their median is also pretty, the 98 percentile is pretty good, 90.8. It's come down a lot. Since we first looked at it. Looking at a bounce rate versus load time, so at this point your bounce rate kind of goes up. If your load time goes more than 6.9 seconds, bounce rate goes to 60%.
Excuse me, what is a bounce rate?
A user comes to your site and leaves after a single page, so we can't consider that a bounce. So the percentage of users that bounce is your bounce rate. If a user stays for more than one page, probably means they were happy with that first page, so they stuck around for the second page. Performance across the day. Something like this typically means that your server is a little busy or something's happening at that point of day. It could mean log rotation. So 8 a.m. UTC is midnight Pacific time.
Which is like 4 a.m. our time, which is like
Yeah.
a bunch of our jobs are running.
So a lot of companies in the US do log rotation when they have fewer users. So it typically happens at night. This is not uncommon for companies in the US.
What do those dots mean?
So that's the median for every minute of the day. So like at 8:16, it's 3.1 seconds median with 1.2 second error. And there are far fewer data points here because it's per minute. So 2 million divided by 1440 and spread across the day. But it kind of tells you, if your things are changing across the day, so are you getting worse during some parts of the day or better?
So there's no two dots that are in the same minute there, or is that just an illusion from?
It's simply because you're trying to fit 1440 points in something that's less than 1440 pixels wide.
Philip, is that any way typical of what you see? I mean, my observation of that is it looks very flat throughout 24 hours.
These are medians. So we're not looking at outliers here. These are medians. If we looked at individual data points, it would be extremely noisy.
But I guess I would have expected, that the morning and afternoon would have a noticeably higher load than
load might
3
increase,
a.m.
but load time may not increase. So the number of data points might change.
Well, that's pretty good, isn't it?
If
for
we
the
look
website?
at this year, we've seen 1,700 data points at that point. Whereas if we're looking at here, there's 713. So that's actually more than double of this in terms of load. But their servers are staying stable, so that's pretty good. Build their systems to be scalable. So, any other questions about that section?
Is that like a month of data, or how
This is a day.
1 day?
Yeah.
Wow. Right, that makes sense.
And like I said, we do all this at break it down by geography as well. So you can then decide your ranges based on different parts of the world and bandwidth. So measure the user's bandwidth and create blocks based on that, and kind of get a distribution from that as well. So you can say, okay, for users for 10 to 100 megabits, how are they performing versus all the other users? Drill down into that as well.
So if we use the log normal, is there a way for us to get the data if we want?
Get the data?
Yeah.
And raw data.
The raw?
The raw data.
Yeah, I mean, we can talk about that if you sign up about getting raw data to you. It's
Probably a lot.
Yeah, I mean, it depends on how many data points you get. The data size may be large.
Philip, you're looking at total page load time?
Yeah, from click to onload.
So do you have any indicators of like like third-party objects or
Not at the moment.
composite stuff?
Not at the moment. So, I mean, you'd have to instrument your code with that. You can actually inject timers into different parts of a page and we get all of that as well. But by default, it won't magically go ahead and do that. Any other questions of this all the top here?
So full page load time, does that include all asynchronous updates to that page? And page
So it's up till onload files, which means if you do things after onload, that won't be measured. Anything that starts before onload typically affects onload time.
Affects what?
Onload time, the time when the onload files.
What's up with IE8 on your graph there? Is that typical of what you see for that browser versus others?
What is it, twice as slow? Yeah, I've noticed that as well. I don't have it.
Yeah, I don't know. I can't say for a fact that it's typical because we've seen sites where IE8 and 9 are the fastest browsers and Chrome is the slowest browser, and we see the complete opposite with other sites. So it depends on the site specifically, not on anything else.
IE8 might imply WinXP, might imply...
It could also mean you're delivering a different site to them. It could be anything.
Yeah, there's a lot of cases where you can have like one piece of JavaScript that performs really poorly in a specific browser.
Yeah. So we've seen a case where a site performs best in Opera Mini. From all the browsers, Opera Mini is the best. And that's largely because Opera Mini, the way it works is the Opera servers download your content, render it as a JPEG, and then send it to the phone. So you're measuring the page load time from Opera servers.
Is there any way for your beacon to distinguish an iPhone 5 and a Wi-Fi from an iPhone 5 on preview?
Yeah, kind of. So,
Other than speed?
well, we do two things. One is this navigated connection with type, which Android devices support, iPhones don't. The other is based on the IP address, get an idea of which so it's AT&T wireless, then you know it's, I mean, that's more or less guesswork. You have to know who the wireless providers are.
How granular would I be able to be within North America? Say I wanted state-specific or city-specific data.
So it depends on how much data you have. Do you want to go into that?
Sure, yeah, go for it.
So, for example, you can see within the US itself across different states. As you go further down, it might get more granular. Not to wait for it.
So I don't know if you're a Tableau user, you might say dimensions. If you're an Excel user, maybe you say pivots. But how many layers? So can you say show me US, IE version 8 or something like that? How many?
Yeah, pretty much what you can do shows up here. So I mean, we could drill down. So depending on the customer, we define different drill down levels. It's like everybody won't get everything. It's like you pay for certain packages and then you can add on things later.
Gotcha.
So yeah, I mean, going back to your question is that like this goes to 1.7 million data points. If I go further down, it might reduce to a point where the error starts going up. At that point, you know, you can't go any further down. So I guess I could go into very few, like there's 1,900 data points from Wyoming.
It looks like you're a little slower in Massachusetts.
That's faster.
That's faster. Maybe zero to
Where's that?
Yeah, our data is awesome.
That's faster. Yeah, darker green is faster.
And we have a ton of people browsing from this office that
like all your users, like 1 million users from the office.
One data that is cached.
Great results. Anything else? Let's switch back